Let me welcome our next speaker, Neelanjan. We are really lucky to have you, Neelanjan, here. You have spoken in great conferences, KubeCon, North America, KCD, Bangalore, and Sri Lanka. So Neelanjan works in Kavos Engineering. I think Neelanjan, take the stage and maybe introduce yourself.
Thank you so much, Humble. Hey everyone, welcome to Kubernetes-Native. My name is Neelanjan and I'm very excited to welcome you all to this meetup where we'll be learning about chaos engineering with LitmusChaos. And it is all about assessing your cloud-native applications resiliency. We'll be taking a look at how LitmusChaos can simplify the resiliency requirements for your cloud-native application and how LitmusChaos can help you to assess the resiliency of these applications with its extensive suite of chaos experiments and help you enable continuous resiliency for your applications. So before we get into the talk, I would like to just briefly introduce myself. I'm a software engineer at Harness, and I've been proudly working at CHAOS-Native, the founders of the LitmusChaos project. I'm also a maintainer of the CNCF LitmusChaos project, which is nothing but a cloud-native framework for performing scalable chaos engineering, which we'll look into more detail. So in my day-to-day work, I'm responsible for assessing the resiliency requirements for any given scenario and authoring chaos experiments that can suitably validate the resiliency of these applications under different real-life parameters. So we'll be trying to see that what these parameters actually look like and what are the parameters on which the resiliency of an application depends and why it matters. We have a packed agenda in front of us. We'll start by understanding the dependency of digital services in the present day context and the challenges posed due to its scale of adoption. Then we'll try to understand the cloud native dilemma and how IT service downtimes can impact a company and your application. Then we'll take a look at what's really chaos engineering and how it can help, along with introducing LitmusChaos in the similar context. Finally, we'll dive into the internals and features of LitmusChaos with also a hands-on demo on LitmusChaos to see how you can use it in order to perform chaos engineering simply. So yeah, without wasting any time, let us actually dive into the roots and origins of chaos engineering and see how it came to be. What really is chaos engineering? So it all started with the digital services. Digital services in 2023. They are more relevant than ever before. And there are a magnitude of reason for this, because you have, for example, these geopolitical issues like, for example, COVID-19 that came. It forced majority of these businesses to go online. And suddenly we have this massive growth of people who are accessing these digital services. Now, the only logical thing for all these companies to do when you have close to 5 billion people who are averaging on an average of 7 hours of digital services every day is to become cloud native. And that's how the cloud native term has come to be. Services that run and scale at a cloud native scale. But now that these services have become cloud native, how can we ensure that they are also resilient? This question is relevant because it's not that easy to operate our cloud native applications. You have multitude of microservices communicating to each other, each serving its own purpose. However, it takes only one of these services to go out and take out your entire application. While the challenges of debugging such an application is a completely different topic altogether, the more relevant point here is businesses should be able to code reliably so that they are able to correctly assess their code in a cloud native environment. And also, it is important because businesses now bring much more new features, more faster, and therefore push much larger code bases much more frequently. So let us try to understand this problem in a bit more detail. So let us understand the issues that we are talking about here with the help of this resiliency pyramid. Our applications, now being cloud native, are actually sitting on top of other services. So you have your directly application dependencies, such as the databases that you're using or your message queues like Mongo, Kafka, you name it. Then you have the other cloud native services such as CoreDNS, Envoy, Prometheus, so on. Lastly, you also have your Kubernetes services like the CoreDNS or any other kubelet or any other Kubernetes components that you have to deal with. Finally, you have your platform infrastructure. So this can be your public cloud, your on-prem, anything that you're using. So as you can imagine, that any one of these services, if they fail, it's definitely bound to take out your entire application. And now this problem is only more apparent because you have these cloud native DevOps, which is kind of trying to replace the legacy DevOps, wherein you used to ship every quarter, like once in a, let's say, quarter. You are just building one application, shipping it every quarter, and then running it. However, now you have 10 times more microservices, which are, let's say, getting shipped every week. And we want to ship them quickly, as well as expect them to run in more environments than ever before, close to, let's say, 100x different environments. And this is the real challenge, that how do we ensure our applications are always resilient when we are shipping at such a huge scale? So before we go to the solution, let's try to see the impact of service downtimes. According to a report by Logic Monitor, companies with frequent service outages and service brownouts, that is degraded SLOs, experience 16 times higher operation costs, need twice as many team members to resolve the issues, and require twice as much MTTR, that is mean time to resolution. However, it should also be noted that the same report found that 51% of these outages were avoidable and 53% of the brownouts were avoidable. However, this doesn't actually cover the full picture. So, of course, like according to ITIC, in 2020, 1 in 4 enterprises indicated that a single hour of downtime can cost their firms anywhere between $1 to $5 million, exclusive of any legal fees, fines, or penalties. But the impact cannot be solely be measured in cost per hour. There are also many potential downsides to outages, such as, according to the respondents of the survey, there are 3 core downtimes, 3 core impacts. So first impact is the external impact, such as loss of customer confidence and damage to the brand. Internal impacts, such as employee morale, affection in the employee morale, and diversion of the resources. And lastly, you have litigations and regulations, which can have a significant effect on any company's valuation. Therefore, the need of the hour is to, if not eliminate, to mitigate the predicament of downtimes. What organizations need to understand is that it's not a question of if, but when will their organization will be affected due to one such big downtime and take out their entire digital services. While one can prepare for the apparent causes that need attention, no one can fully anticipate an overwhelming downtime before it actually takes place, because there are so many different ways in which things can go wrong. So with the entire applications and their underlying infrastructures now evolving at the pace of hours and minutes for the much needed competitive edge, how do we ensure that our distributed systems always withstand the chaos of adverse situation? Well, by breaking them on purpose with chaos engineering. So what is chaos engineering? It is nothing but a way to go for all those enterprises who want to prioritize resiliency and reduce downtimes for their customers. So how do we do it? Well, it is a culture-oriented approach. It is about adopting a culture of building resilience against unforeseen challenges with their systems. So the way it works is, first you need to fully understand your system. You need to understand how your system behaves under normal conditions, under stressful conditions, how the different turbulent conditions might affect your application. And of course, they should be based out of real world scenarios and not just synthesized lab parameters. The key to successfully practicing chaos engineering is to understanding the complexity involved in your system through realistic experiments and hypothesis conditions. Only by fully understanding the pros and cons of your system will you be able to choose the right chaos experiments. So now actually speaking a bit on the process of performing chaos engineering, it's nothing but you can say it's divided into 4 or 5 different steps. The first step, as I said, is to understand the complexity of your system, understanding what actually your system looks like under, let's say, into a stable situation when, let's say, your system is working correctly. After that, you will hypothesize what are the different factors that can affect your application. Now, there can be, of course, many different factors that can cause outage for your application. Once you have your hypothesis in place, you actually go on to perform that hypothesis using the chaos experiments. Here, you are mindful of how much harm or chaos you want to inject within your application. And based out of this experiment, the results of the experiments are then used to evaluate whether your application is standing up to the hypothesis that you had or not. That is, whether it is actually fulfilling the hypothesis that you had set it up for or not. So if it is if it is actually passing on those hypotheses, then well, you have a very resilient application and you are ready to go for your deployment. But let's say you are actually finding a weakness in your application, that if your hypothesis is not valid yet, you can go on to again fix your application. You can try to fix the problems that you found with your application and try to then again perform this entire cycle, that is understanding your steady state and performing the experiment based on a hypothesis and so on. So that's how we kind of enforce the resiliency into our application. And this needs to be done from a very nascent stage of an application building, like starting right from the dev to all the way to the prod. The entire culture should shift left and basically try to include resiliency into your DevOps pipeline. So yeah, that's basically how chaos engineering looks like in theory. So now, what are some of the best practices of chaos engineering? What does a good chaos engineering practice looks like? So as I said before, it's a culture-oriented approach. And the best way to inculcate a good chaos engineering culture will look something like this. So first of all, you need to take chaos engineering as a collaborative activity. That is, SREs and developers should work in collaboration. While developers should focus on left shifting resiliency by performing chaos experiments early on in their development cycle, SREs should try to scale up these experiments so that they are available to be performed in the prod environments, let's say. Then, of course, you should have a robust set of experiments. You need to have all the different kinds of failures that you would want to perform into your application available to you. Then, of course, you would want to perform chaos into CI/CD because you want to always be aware about the resiliency of your application, because as we discussed right now, we are shipping code more frequently, and what can be the best way to integrate your chaos experiments as part of your CI/CD pipeline, because that way you will always be assured that you are shipping resilient code. Lastly, you need to enable observability for chaos, because as I always say, without observability, chaos engineering is simply chaos. You won't be able to figure out what component of your application is actually weak if you don't have proper observability with your application. So yeah, that's kind of a very compact way of describing a good chaos engineering practice. But well, now you must be thinking that how would you actually bring in a good chaos engineering culture in your organization? Because these are only some of these aspects that needs to be there, but it's actually a whole lot of effort when you will see to inculcate a whole culture. But that's where LitmusChaos comes in. LitmusChaos can help simplify your chaos engineering journey. So LitmusChaos is a tool set to do cloud native chaos engineering. It helps both developers and SREs to automate the chaos experiments at different stages within their DevOps pipeline, like development or CI/CD or in production. Fixing the weaknesses leads to increased resiliency of the system. And that's the idea that chaos engineering brings in. Litmus adopts a Kubernetes-native approach to define the chaos intent in a declarative manner. That is via custom resources. It uses the operator pattern and relies on custom resource definitions, that is CRDs, to perform these experiments. So on top of that, Litmus also provides a well-rounded UI called the Chaos Center dashboard, which we'll see in a minute. And also, it is used for orchestrating and visualizing the results and metrics of the conducted experiments. It also features a Litmus API for programmatically injecting and managing the chaos, features for teaming and collaboration, GitOps management for chaos, Chaos Hub, which we'll also touch about in a bit more detail in a while, which is like an open source marketplace for all the chaos experiments. Finally, it's also worth mentioning that Litmus Chaos has seen tremendous growth and adoption in the major enterprises dealing in all kinds of technologies, further validating the need of chaos engineering and its versatile applications in all the different kinds of technical domains. So with that, let us actually try to understand how Litmus Chaos works. This might be a bit more tech savvy, bit more challenging, but yeah, just feel free to ask any questions that you have. But yeah, when you see Litmus Chaos, it's actually split into two parts. You have your chaos control plane and you have your chaos execution plane. The chaos control plane is nothing but the user facing component through which the user can schedule different experiments. They can visualize the different experiments as well as interpret the results of different experiments. As part of this, you have the chaos center. Now, chaos center is of course the UI through which you are scheduling your chaos experiments. So more than that, it also contains the Litmus API as well as the Litmus CTL, the command line utility. So we'll see about those in a minute. But yeah, they are actually talking to the auth server, which is well for the purpose of authentication, and we have a Mongo database for that. And also we have the GraphQL server, the central server that is actually handling all of your queries with regard to how chaos engineering has to be performed. So what we do essentially, whatever we learned that we are using CRDs in order to perform chaos, we are kind of using the chaos center to create those CRDs, as we'll see. And then after the creation of the entire manifest, we give it to the GraphQL server, which then takes the CRD to the chaos execution plane. Now, again, in chaos execution plane, we have three parts. As you can see, we have the agent infra, we have the backend execution infra, as well as the application stack under test. So we can safely ignore the third part because that is our target applications. Of course, they are the one getting affected out of the chaos, but let us actually deal with the first two parts, that is the agent infra and the backend execution infra first. Inside the agent infra, we have different components such as the workflow controller, the subscriber, event tracker, and chaos exporter. Starting with the subscriber, that is kind of the point of contact for the GraphQL server from within the chaos execution plane. It ensures that a connection is maintained always between the chaos execution plane, which can be actually be remote. Yeah, so I guess I should have just made that clear first. Chaos execution plane can be either inside the same cluster where your chaos control plane exists, or in a different cluster that is a remote agent, you can say. So of course, chaos agent or the subscriber, that is kind of the point of contact for our chaos control plane, which establishes this connection. It receives all the requests or the responses that are coming from or to the GraphQL server. And then it basically receives all the manifests that we need to create as part of injecting our chaos, as well as it sends back the logs and results of our chaos back to our GraphQL server. So upon receiving the workflow manifest from our GraphQL server, what the subscriber does is it kind of creates this chaos workflow custom resource. Now, the chaos workflow custom resource is nothing but an Argo workflow. If you know Argo workflow, that is basically a declarative manner in which you can define and run your Kubernetes workloads, right? So that is how basically you are creating your Argo workflows. Now, inside your Argo workflows, you have the different parts of your chaos experiment defined. You have the chaos experiment custom resource, which is nothing but it contains the low-level information with regards to your chaos experiments. It contains all the various parameters that you want to use, the image, the Docker, the container image that you want to use for the purpose of chaos, and so on. And also the chaos engine custom resource, which is kind of the central component, which is reconciled by the chaos operator. So chaos operator is the heart of Litmus Chaos. It is the operator which kind of reconciles the chaos engine custom resource to kind of create these Kubernetes jobs, inside which our chaos intent is converted into actual source code logic and executed to perform the faults. So yeah, that is a gist of how Litmus Chaos kind of works. Don't worry, we'll be actually be seeing a hands-on demo, and I'll try to again elucidate parts of it. But yeah, with the remaining parts of the agent infra, we have the event tracker and the chaos explorer. So event tracker comes at parts as a part of the backend SCM, Git SCM. So here what we do is we kind of enforce the GitOps logic, wherein we use Git as a single source of truth for all the manifests that we use for the execution of the chaos. So whatever manifest that is being given to us by the GraphQL server, that can also be stored into Git databases directly instead of our Mongo database. And whenever any changes made to that Git database, we can essentially trigger a chaos experiment for that. So this is for that purpose. Event tracker helps us for that purpose. Lastly, we have the chaos exporter. So that is again related to the observability. As I said earlier, without observability, our chaos engineering practice is not enough. So what chaos exporter does is it exports relevant information with regards to our chaos experiment in a Prometheus format. So a Prometheus time series database will be able to consume those metrics, and it will be helpful for the visualization of the experiments. So how does that look like? I'll show you just in a minute in our demo. So yeah, I had prepared many more slides actually on chaos, on the features of LitmusChaos, but I'll try to skim through them because anyway, we'll try to see how it looks in real life. So yeah, we have actually many features with regards to chaos, LitmusChaos, such as the Chaos Center first. Inside Chaos Center, the primary thing that you'll be, of course, be interacting with is with the chaos workflows. As I explained, chaos workflows are a way to kind of knit together different chaos experiments. So you can set up all these different faults in any order or sequence that you like using your different chaos workflows, like in parallel to each other or serially one after the other. You can do all that. Then you have multiple options of creating these workflows, such as you can just upload your manifest, since it's just a declarative way of defining your chaos intent. So it's essentially just a manifest in the end. You can directly upload it, or you can use the hubs in order to create your experiments, so on. You also have control over the sequence, as I said, like you can create parallel or sequential chaos experiments in a workflow. You can also define schedules, like let's say you want to run a chaos experiment as per any cron sequence. So you can define that sequence and according to which the experiment will go on. And then we also have the experiment priority, like, you can assign different weights to an experiment. We'll come to the concept of resiliency score into our demo as well. Then we have backend GitOps. As I explained, we can use Git as a single source of truth for storing all of our manifests and then triggering chaos according to that. We can use custom images. So that is really beneficial. Let's say when you're executing your chaos in a air-gapped environment where you're not really connected to the public internet. Then, of course, resiliency score is something that we use for the assessment of how successful is our chaos experiment. We'll see that in our demo. Then we have the concept of multi-tenancy as well. So let's say you want many people to kind of access your cluster, and you want to restrict the amount of scope that you want to give to your LitmusChaos. Because let's be honest, guys, this practice, chaos engineering practice, is a very disruptive practice. You are kind of exposing your applications in a way of harm, you can say, by injecting these tests. So it's very essential to be to ensure the safety of these applications. So Litmus allows you to kind of restrict itself to only a namespace with using a namespace scope installation, and you also have cluster scope installation. So the difference is, like with namespace scope, you can only inject chaos in that same namespace where you're installing LitmusChaos. And with cluster scope installation, you can inject chaos in any namespace that you want. On top of that, you also get the authentication. You can create different teams within LitmusChaos. Also, you have fine-grained RBAC for each and every experiment. So how does that works is, if you are aware of the RBAC API, LitmusChaos uses that to kind of granularize each and every permission that it will leverage for each and every fault, and kind of use only that much amount of permissions while not using anything more than that. So that kind of restricts what your application is, what your chaos experiment will do in the cluster. Again, we have much support for monitoring and observability. We'll actually see all this in a while, so I'll just skip this slide. Also, we have GitOps for chaos. So as I touched on it, Git-based SCM is providing the single source of truth for chaos artifacts. Like we can store all of our manifest within the Git database and kind of use them to trigger our chaos experiments whenever there is a change in it. And it also helps you integrate better across your team, because your Git manifest can be essentially be shared with a hosted Git option like GitHub or GitLab or something. Then event tracker, as we said, event tracker is basically an advanced feature which helps you to kind of monitor for the changes in a defined cluster. And we can define an event tracker policy. So that event tracker policy will essentially define a certain condition that should be fulfilled within your Kubernetes cluster. So it defines the state of a cluster in a declarative manner. And if that state of a cluster is matching what's defined in our event tracker policy, then we'll trigger a chaos workflow. So that is kind of, again, a GitOps oriented way of injecting chaos and managing chaos. Lastly, we have non-Kubernetes chaos support as well. Of course, chaos is not limited to Kubernetes. Cloud native application deployment goes beyond Kubernetes as well. So we can do chaos on infra like GCP, AWS, Azure, VMware, virtual machines, disks, many other infras as well. And you can also target your bare metal nodes, IPMI based access nodes. You can definitely perform chaos on that. Lastly, we can also target chaos on machines using something known as M-agent. So it is basically a platform generic daemon agent, which kind of orchestrates chaos into any computing node using LitmusChaos. All right, I have said enough. Now we'll look at actually what LitmusChaos looks like in action. So yeah, I'll be exiting my presentation and I'll try to share my browser window now. So I'm hopeful that you are actually able to see my browser window. And what we are going to do today as part of this demo is we'll be actually be talking about the different things that you can do with LitmusChaos. We'll see that how LitmusChaos can be used for creating these different chaos experiments in a very simplified manner. So in the interest of time, I have actually already installed LitmusChaos. As you can see, this is the UI. We'll be logging in shortly. But more importantly, what we are going to do today is we'll be trying to take down, or rather, just assess the resiliency of this microservices application known as Online Boutique Shop. So Online Boutique Shop is nothing but an e-commerce application, a demo microservice application, which is, of course, deployed in Kubernetes. It has a microservice architecture, of course. So you have all these different pages like this product catalog page. Then you have this cart page. You have also different product page, so on. So each one of these is actually a microservice. There is a payment gateway as well. It's all a microservice. And we are also having a Grafana dashboard over here, which is actually visualizing the state of this online boutique application. So what we see before us right now is the present state of the application. And as you can see, we have the names of different microservices here, like the front-end microservice, the cart service, the product catalog page, the checkout service, the ad service, so on and so forth. And from what I see, it looks like our application is in a healthy state right now. The access duration, or you can see the latency, is kind of it's not deviating that much. The standard deviation is very less. Actually, it's like more like 2 or 3 milliseconds, which is okay. And the QPS, that is queries per second, whichever one we are making, the green points are actually signifying the queries per second, which have been actually responded to. That is the queries which were actually served, while the yellow is the 99 percentile line, which depicts the queries, which the rate of failure of the queries, that is the queries that were not responded. As you can see, if I just hover over it, the formula, or basically the command that we are running as part of the Prometheus, that kind of depicts the 400 status code. It is looking out for 400 or 500 status code. So yeah, anyway, that basically gives you an idea of how our application looks like right now and what these graphs depict. So the importance of this graph is we'll be using it in order to assess the state of our application at different stages as we perform our chaos experiment. So yeah, we have already achieved the first goal. Our application is right now in a healthy state. So the next step is actually go ahead and hypothesize what can go wrong with our application. But yeah, before we do that, I would like to actually show you how our application looks in real life. I hope my terminal is visible. So yeah, I'll just try to list down the pods of this application. We have installed this application in this namespace called Boutique. I'm just using aliases, by the way. KG is just short for kubectl get. So kubectl get pods in the Boutique namespace. Here we can see that we have the different microservice pods here with us. So yeah, all good. We have one replica of each pod, as we can see. I mean, we can also do a deploy for that. As you can see, we have one replicas of each microservice right now, and they all seem to work correctly. But let us hypothesize something. We can obviously see that there is a problem over here. If any of these replicas goes down, will our application be still resilient? This question is valid because, well, pod deletes are a very frequent event in Kubernetes world. So if we actually go ahead and let's say delete one of these pods, what will happen? And that is where LitmusChaos comes handy, because you can actually perform this experiment and check upon this hypothesis to actually find out what will happen if you do that. So let us actually try to find out what happens when we actually, delete one of the replica pods of this carts microservice. That is the experiment that we'll be performing today. So as you might have already guessed, we are going to perform a very common experiment today, a very popular experiment called the pod delete, which is kind of a cliched experiment, I would say, because everyone talks about it, I would say, but still, it's a good learning point for us where we will see how LitmusChaos works. However, I should also mention that LitmusChaos is not, of course, limited to pod delete. We have more than 50 chaos experiments which can validate a host of different chaos scenarios. So I'll just touch upon that. As I had promised, here's the Chaos Hub. As we defined earlier, Chaos Hub is nothing but an open source marketplace for all these chaos experiments that we have. The reason is that, of course, this is the Chaos Hub which is provided to you by LitmusChaos. However, let's say in your organization, you are having your own chaos experiments for your own personal purposes or like for your organization's purposes. So that you can also maintain, distribute, and manage using these Chaos Hubs. So in the background, Chaos Hub is nothing but a Git repository, which is kind of storing all these manifests for the different chaos experiments. And that's what makes Litmus so much extensible and powerful, because you can extend it in any way you want. It being open source is only a cherry on top of the cake. So yeah, let's actually right now take a look on all the chaos experiments that we have here. You can see we can do pod network-based experiments such as network loss, network latency, all the host of it. And you have HTTP based experiments, you have DNS based experiments, you have node level experiments such as node restart, node network latency, so on. By the way, we also have some OpenEBS experiments. Throwback to the time when LitmusChaos was started. It was actually started as a way to assess the resiliency of the OpenEBS project, which is also a very popular storage orchestration project in the CNCF space. But yeah, currently we have more than 50 experiments, as you can see. So yeah, enough with the Chaos Hub. You can actually go to hub.litmuschaos.io to check out all the experiments in detail. But we are right now going to perform the pod delete experiment. So how do you do that? Well, first of all, I reflected on this earlier that you can either install LitmusChaos in that same cluster where you are performing your experiments, that is where your chaos center is installed, your control plane is deployed, but you can also connect remote clusters using LitmusChaos. So this is currently our cluster where we have already installed our chaos center as well. That is the chaos agent and chaos center are in amalgamation. They are in the same cluster. So I can actually try to show you guys through my terminal again. If I do pods in the Litmus namespace, you can see that we have like all of these pods running for LitmusChaos. So here only we have all these different components that we are seeing earlier into our presentation. So yeah, that's how we have our chaos delegate. That is the self delegate in this cluster. So now our application lies in the boutique namespace, and the service that we are interested in the deployment is the card service. So let us see how we can define a simple pod delete experiment for this. Let me try to schedule a chaos experiment. I'll choose the self agent that simply corresponds to this Kubernetes cluster in which LitmusChaos is installed. And our application also seems to be installed. So I'll just select that and choose next. I'll be choosing Chaos Hub because as we saw, like all of our chaos experiments are there. But yeah, right now we have only one Chaos Hub. And as I explained, you can have multiple Chaos Hubs as well. Then I'll simply choose next over here and say, let's say cart service bot kill. Give it the same description, I guess. Choose next. So here you have a graphical depiction of what your chaos experiment will look like. As you can see, we have no experiments here, but we are interested in the pod delete experiment. So I'll just go ahead and select the pod delete over here. Upon adding the pod delete experiment, you can see that we have added this step of the pod delete serially to the install chaos experiment step. Now, the point to be noticed here is we can add more chaos experiment on top of it here. And we can actually add them in any sequence we like, either in sequence to pod delete, like serially after the pod delete, or in parallel with pod delete as well. So that is the handy feature that chaos workflows provide you. You can string together different chaos experiments to create a robust or like very niche chaos scenario out of it. But anyway, we are only going to perform the pod delete today. So let me try to kind of edit this experiment so as to provide it the actual like target and other stuff. So if we select our application namespace over here, we are actually looking forward to. Okay, I guess we have some questions in the chat.
Yeah, I have posted one question, Neelanjan. Yeah, so I'm just wondering, like, I mean, who will be responsible for generating these experiments? Is it developers or the platform engineers or SREs or?
Okay, so that's the idea that we take forward. We kind of scale it from left to right. We always try to inculcating the culture of left shifting chaos, such as developers should try to introduce the chaos experiments early on in their pipeline. They should try to run these chaos experiments as frequently as they can while they are starting with the development. And also the SREs should try to scale these chaos experiments so that they are running in the, let's say, pre-QA or in the QA environment, and finally in the prod environment as well. The idea is to start small, then try to make sure that your experiments are scaling up. You are ensuring that your experiments are always incrementally increasing in blast radius bit by bit. And we need to do so as to not harm the services that are already deployed. So that's the idea. It's for everyone. It's not just for the prod. It's not just for the DevOps. It's not just for the SREs or the developers. It's a whole culture that we are taking forward.
Great.
Awesome. Okay, so back to the demo. Let's see.
Neelanjan, this is Prasad. Can I ask one question, please?
Yeah, sure.
Okay, so is there any marketplace or the repository where we can browse the existing chaos recipes? Is something like that available?
Yeah, right. So as I mentioned, you can go to hub.litmuschaos.io. Actually, I can just quickly show you. So hub.litmuschaos.io is the chaos hub that I showed you earlier. It is nothing but all of these experiments that we saw before. This is the chaos hub, which is directly provided to you by LitmusChaos, and it contains over right now, let's say around 50 experiments that you can use for your chaos experiment purposes. And it builds on this extensible approach, right, that I explained. That this is not all. I mean, you can also have your own custom chaos hubs, which you can use to kind of share and manage chaos between your organization. That is like a private chaos hub that we are talking about. So this is a public chaos hub.
And Neil, are these agnostic or are these specific to the Litmus? or I can use with other frameworks also? Chaos framework.
No, no, you can say that these will only work with Litmus Chaos because these have the entire, these are nothing but charts actually. I mean, if I try to open one of these, let's say. So if I try to open one of these, this is nothing but charts, right? And these are CRDs for different Litmus Chaos components. So it will only work with Litmus Chaos. That is what I'm trying to come at. These are CRDs.
Sure, thank you.
Yeah, sure. Okay, going back to the demo actually. Okay, I guess we have a little bit of a hiccup here. Okay, we have a little bit of a real life chaos going over here. Just give me 1 minute. Sorry for this. All right. How about we start off again? This is what happens to me all the time. I try to perform live demos and we expect hiccups. But yeah, all good. I guess we are good now. One of the pods went into not available state. All right, awesome. We are back on track. So this is the thing actually that I want to show you. Litmus Chaos is able to actually kind of discover all these namespaces and resources that we have. So if I kind of edit this experiment and if I click on the app namespace, because this is where you'll specify your target application. So if I click on application namespace, we need to specify the namespace wherein our target deployment lies. So that happens to be boutique because we saw earlier all of our application, all of our boutique application is deployed in the boutique namespace. So I'll choose that. And our app kind is definitely deployment. But yeah, these are all the options that we have. Stateful set, daemon set, etc. You can also target. And now comes the app label through which Litmus Chaos will be actually targeting the application pods. So if I quickly go back here and kind of try to show you the labels that we have. So we can see that the cart service has this label of app is equal to cart service. So that is how we'll be specifying this cart service to Litmus Chaos. So I'll be just choosing this label. Now, of course, it is important, and as you might already know, the same label should be also be present as part of the pods of this microservice or this deployment. So that is the case, actually. I'm not going into that, but yeah, this pod that we saw earlier, this cart service pod, this is also containing the same label. Back to the demo. So here, app is equal to cart service, we have completely provided our chaos experiment, our target application. So let's go next. And here we need to add a probe. Now, we didn't actually talk about the concept of probe earlier, but this is a central principle or like a very pivotal concept of Litmus Chaos. So probes are a way to kind of declaratively define the chaos intent. You can basically use it to automate the process of hypothesis checking as part of a chaos experiment. Or simply speaking, it allows you to validate any condition that you want to test throughout your experiment duration. So let's say while you're creating your experiment, you want to check whether your application pod, for example, that happens to your cart service, whether it is available or not, because cart service is what is actually enabling this page. This is actually the /cart endpoint. So you want to validate whether this endpoint is available or not. And the way you do it is using this cart endpoint, using this probes. So how can you do that? Well, let's say I want to add a new probe. I'll just simply choose the cart probe over here. And then we give some probe properties, like let's say this is an HTTP probe. We have a command probe as well, but since this is an HTTP probe, what is the timeout of the HTTP request that we are performing? So let's say 2000 millisecond is my timeout. And how many retries should I perform if my if we are not able to actually hit the endpoint that we are trying to do? And then we have an interval as well, like how after what duration should we put this request, HTTP request, to our endpoint. So let's say that can be 1 second. And probe polling interval, this is only relevant in case of a continuous probe. As you can see, there are different modes of the probe. SOT probe will only run in the beginning of the test. EOT probe will only run in the end of the test. Edge mode will run in the start and the end, like SOT and EOT combined. Continuous will ping this URL in a continuous manner throughout the chaos experiment. So that is the idea behind these modes. We'll just choose continuous actually and give 1 second over here. And now comes the URL that we are interested in, that is, which is the URL that we want to monitor as part of this chaos experiment. And I'll choose here frontend.boutique.svc.cluster.local/card. Now, what is that? Well, we saw earlier that, okay, I should just list down the services that are present in the boutique namespace. So here we have this card service cluster IP service, which is kind of the go-to endpoint for the card service, right? So here I'm using a Kubernetes FQDN to kind of specify that card service endpoint using its DNS and with a /cart endpoint. So the point that I'm trying to make is this will help us to validate whether this cart endpoint is available or not. This is how we are actually checking for that endpoint through this URL. And lastly, we need to mention the criteria that we want to validate for, like whether if we are making a GET request at this URL endpoint with these parameters, with these like configuration, I'm always expecting a response code of 200. And if I'm not getting a 200 response code, then I should mark this experiment as failed. That is the central idea of the probes. You can attach these conditions, these declarative parameter checks as part of your chaos experiment that will help you to validate the resiliency of your application. So yeah, in interest of the time, I'll just stop explaining this even more. But yeah, you can add more probes actually. That is how it goes. But yeah, that's how your probes will look like. And now for configuring this experiment, well, we have our tab here. So here we have different parameters for the experiment, such as how long the chaos should go on. So let's say 60 seconds. For 60 seconds, we'll be running the pod delete. And at what is the chaos interval? That is for how frequently should we delete the application pods. So as you know, I mean, pods will again come up, right? So how frequently will we keep on deleting these pods for 60 seconds? So that should be 5 seconds. At every 5 second delete my card service pods. And finally, the pods affected percentage. So let's say that I'll give here, we can just leave here empty because, or we can give it here 50% as well. It is actually a max function of 1 comma whatever pods we are filtering out of this percentage. So in minimum, it will be selecting 1 pod only. Since we have only 1 pod here, so it doesn't really matter if we give here 50 or even leave it empty. It's going to take 1 pod only. However, I'll again come back to this. Then 50 will be beneficial. We'll see how it will be later beneficial. But yeah, for our practical purpose right now, we'll be only be targeting that 1 pod here. So let's go next and actually finish here. We are quite done here. We'll go next. And yeah, this is the resiliency score. This is what I was trying to define earlier. Resiliency score or the chaos weights over here, which is useful in the calculation of resiliency score, is a point that you assign to a separate experiments in a chaos workflow. So if you want to, let's say, assign different level of importance to each one of these chaos experiments, you can assign it by doing so. Now, on the basis of this point, in the end, you will get a resiliency score. That score will be a measure of how resilient your application is when this experiment is performed or when this scenario is performed. So yeah, that's where resilience, that's where these weights come in. Okay, so I'll just go on and next to the schedule tab, that is when I want to schedule it right now. Next. And then finally, okay, so this is the end. I mean, we can just right now finish here. So now, as you can see, that's it. I mean, of course, I took a long time explaining it, but it's as simple as that to get started with your chaos experiments using LitmusChaos. It's a completely declarative way. By the way, I forgot to show you how the manifest looks like, but let me just try to show you. Oh, okay. Bad one. let me just show you how the manifest looks like that I was talking about earlier. So this is how the workflow manifest for the entire experiment looks like. You have a chaos experiment custom resource embedded within this Argo workflow. So chaos experiment is a custom resource which will now go ahead and get installed within our cluster. It contains all these parameters that we just configured earlier. Please ignore these parameters because there is another custom resource that we are also installing, chaos engine custom resource, as we saw earlier. So this is kind of having the granular details such as the application namespace, that is the boutique namespace, or the app label or the app kind. And then we have all these env parameters such as the time of the experiment, that is 60 seconds, or the interval, or the pods affected percentage, and also the probe that we had defined over here with that URL. So yeah, that's how it looks. So now let us try to visualize this experiment and how it is looking like. We can see that our application is already working. And now if I try to refresh our application, okay, it's still available. That is good. The pod delete has actually started. And if we head over to our dashboard, we can see that our Grafana is getting annotated over here. And we can immediately see that there is a huge dip in the probe success percentage of our application. So probe success percentage is nothing but a measure of how available our application is when we are actually making a GET request to the pod to our endpoint, how much it is available. So we can see that is taking a dip. And at the same time, our cart microservice, the QPS for our cart microservice is also going up, and the number of failed requests for that is like 400 or 500 like status code requests, that is also increasing. This yellow line is increasing. And this annotation, as soon as the chaos experiment started, this annotation came over here. That is by virtue of the chaos exporter component that we talked about earlier. It's nothing but a Prometheus annotation that we are kind of importing it over here. So now if we actually try to reload this page, we can immediately see it is giving us a 500 internal server error. And this is not very surprising. We had only one application pod. By virtue of it is actually failing. Because that pod is not available right now, it makes perfect sense that our application is kind of going through this where if we are deleting that pod, our application is not available, it's having this 500 internal error. And this is how we are actually finding about it. So yeah, that's one leg of the way in which you can use chaos engineering. Since we have a time check, we are already over time. I would have wanted you to show by increasing the number of pods and scaling up the cart service microservice, and then running the same experiment again. Then you would have seen that none of this would have happened. In that case, we would have still have a replica of the pod available with us if we kill only one out of the two pods. And that's how our application will become more resilient. You can say that even if one pod out of the two pods, or 50% of our pods are not there, our application will still sustain because there will be at least some replicas which will be there. So, but yeah, let's maybe not go into that since we are over time. This is a brief introduction to how you can use chaos engineering in order to make your application more resilient, you can say. I'll just take a few more minutes to show you that now that our chaos experiment is almost complete, what has happened. So first of all, if I try to refresh my application, you can see that it's again back, which makes sense. The deleted pods have come back. We can already see that in our monitoring dashboard, the metrics are becoming more normalized and it's regaining its normal system metrics. And here we can see that this experiment has failed. So let us try to see why has it failed through its logs. So if I go here and try to check out the logs of the experiment, we can directly we can start from here. So if we just try to follow the logs, we can see that all the target information is here, like namespace was boutique, kind is deployment, and the label is app cart service. And we are performing the chaos for 60 seconds and so on. Now, our probe information is also here. So we can see that we are kind of running it for 2000 millisecond for, at an interval of 1 second and so on. It's a continuous probe and stuff. And the URL that we wanted to validate was this. Finally, we have, a successful run of the probe as well. I mean, initially you can see that when the probe was run, the actual value was 200 and the expected value was 200 as well when this URL was pinged. So that therefore passed because these values are equal. That is what we were expecting, a 200 status code. However, when we actually started our experiment, by the way, you can see here that this pod, this is the name of the pod that was initially filtered. This is the one that we'll be deleting as part of this experiment that was filtered here. However, as soon as the experiment is actually started, you can see that when we made this probe request, our probe has actually failed over here. The probe get method has failed and the probe has responded with an invalid output, that is a 500 status code. However, we were expecting 200 status code and hence the probe has failed. So that is what eventually led to the failure of the experiment at the end of the total experiment duration. And that is how we came to the conclusion that our application is in fact not resilient. Our application has a weakness. And Litmus probes is therefore helpful in validating this entire scenario with the help of this declarative and automatic check. So yeah, with that, I would like to actually wrap up. I hope this gave you an insight into what really chaos engineering is, how resiliency can affect your application's behavior and why is it important, and how LitmusChaos makes it super easy to get started with chaos engineering and adopt a healthy chaos engineering culture in your organization. So yeah, that's it from my end. Thank you so much.
So we have more contributors to the LitmusChaos project. That's really great. Yeah. So once again, thanks a lot, Neelanjan. You have given or proved once again you are a good speaker.